So I do need to do that. But yeah, I'm thinking, let me, oh, there it goes. It does it right when I'm about to give up. So let's try again. Okay, fingers crossed. If not, gotta go to the camera. Okay, so two events that have no influence on each other. That means that knowing one event occurs has no influence whatsoever on the second event. So for example, if you flip a coin twice, that's technically two events, because event A would be that the first flip comes up heads. Event B is that the second flip comes up heads. These have no bearing on each other, okay? If my coin comes up heads on my first flip, my second flip still has a 50% chance of heads. The probability does not change. Knowing that the first flip was heads right here does not have any influence on what I believe is going to happen on the second flip. In fact, if you flip a coin 10 times in a row and you get heads all 10 times, what's the probability of getting heads on your 11th flip? So my coin came up heads 10 times in a row. What's the chances of heads? That's still 50%. So there is no idea that, you know, oh, wait a minute, it's supposed to be 50% overall. I've had heads 10 times in a row. I think this coin is due to come up tails. It doesn't work that way. Coins have no memory. The coin does not have a brain to say, hey, you know what? I came up heads the last 10 times. Maybe I should make sure that I come up tails because I haven't come up tails in a while. Coins do not have any memory of what has happened in the past. The events, even 10 in a row, has nothing to do with what the 11th flip is going to be. These are completely independent. Okay, so these are independent. Okay, so this one right here is a probability of 0.5 no matter what happened on the first flip. Okay. There's a couple events that we can decide, even though we don't know the actual probabilities of them, you can probably help me decide whether you think they're independent. So two events. We got a person driving on an I-80. Event A is that the person is speeding. Event B is that that person gets stopped by the CHP. So if I tell you, A, this person is speeding, do you think that should change the chances of them getting stopped by the CHP? So does the fact that somebody is speeding affect the probability or the chance of them getting stopped? Yeah, I think it should. In other words, you would hope that a person that is speeding has a higher chance of getting stopped compared to someone who is not. So if I say, hey, somebody was stopped by the CHP and I tell you, you know, that person is speeding, that increases the chances of someone getting stopped. So we would say that these are not independent. In other words, if A, the person was speeding, even though I don't know the actual probabilities, I think it's safe to assume that I would expect the probability of them getting stopped by the CHP is going to increase. Okay? Two cards. You pull them from a deck without replacement. So knowing a little bit something about cards, there are 52 cards in a deck, and there are 4 of each type. So like there's 4 2s, there's 4 3s, there's 4 4s, etc. Because there's one, each number has a heart, a diamond, a club, and a spade, just kind of real roughly here. So if you have a deck of cards, the probability of pulling an ace out of a deck, there are 4 aces out of 52 cards. So the probability of pulling an ace out of a deck is 1/13. It's 4 out of 52, which is 1/13. And we are on a drag again. This keeps up. There we go. Now the second card. Pulling a second ace out of the deck. is it still 1 out of 13 if I told you the first card was an ace? So I pulled, A happened. The first card I pulled was an ace. We are doing this without replacement. So I'm not going to put that card back in the deck. What's the chances now of me randomly pulling a second card out of the deck and having it be an ace? Did it change? Yeah. Yeah, we have only 3 aces left. There are not 4 aces in my deck anymore. There are 3, and there are 51 cards in the deck. Now, 3 out of 51 is very close to 1/13. It's very close to 4 out of 52, but they're not the same. If the first card I pulled was not an ace, that probability would be different because I'd still have 4 aces. So in other words, the first card changes what happens with the second card, changes the probability of it. So these ones are not independent. When you pull one card out of a deck, it affects the chances for the second card because you now have less cards in the deck. Okay, so first thing you need to know is just, what does it mean for 2 events to be independent? And it literally just means that the first event has absolutely no influence on the second one. Okay, the second type of events are called mutually exclusive. Your book refers to them as disjoint, but the AP exam calls them mutually exclusive more often. So just know that they are the same thing. But mutually exclusive events or disjoint events are events that cannot occur together. So they cannot occur at the same time. So now we're talking about 2 events occurring together, whether or not they can occur together. So this is not about independence. It's about whether 2 events can occur together. So let's say I select one Whitney High School student at random. I'm only going to take one student. Event A is the student is a freshman. Event B is that same student is a senior. Can both of those be true at the same time? This is one student. So can you have one student who is a freshman and at the same time that same student is a senior? Nope. Year in high school are mutually exclusive. You're either a freshman, a sophomore, a junior, or a senior. They are mutually exclusive. Okay. Now, if event A is that the student is a freshman and event B is that the student is a male, they are not mutually exclusive now because you can be both. But these ones are mutually exclusive. You cannot be a freshman and a senior at the same time. So these are an example of mutually exclusive. Okay, and then down here, notice it says disjoint events or mutually exclusive events are never independent. Okay, meaning I'm going to pick a person at random from Whitney High School. I tell you, the student is a freshman. Does that change the chance of them being a senior? So I pick a student at random from Whitney High School. I tell you, this student is a freshman. What's the chances that they're a senior? Don't overthink it. What's the chances that they're a senior? 0. Now, if I don't tell you this, if I say I pick a student at random from Whitney High School, and I just say, what's the chances they're a senior? It's not 0 now. Now it's however many seniors there are out of, our student body of like 2,000. It's not 1/4, 1/4, 1/4. There are less seniors than there are freshmen, for example, but it's probably close to, 20% or something like that. So I now could calculate the probability that the student is a senior by taking the size of the senior class and dividing that by the size of the entire student body. And it's not 0. However, if I tell you that the student is a freshman, the probability that they're a senior is 0. It depends on what I tell you about that student. If I don't tell you anything, I get a different probability than if I tell you that that student is a freshman. So they're not independent, and that will always be true. So if they're mutually exclusive, they'll never end up being independent. It's not that they really have anything to do with each other, but that's just the way it will always work out. If I tell you I flip a coin and it came up heads, the probability that it is tails is 0, because it can't be both. Anything that's mutually exclusive, since it can't be both, if I tell you that it's one thing, then the probability is 0 of the other, because they cannot be the same together. Okay, on the next page, these are just some basic probability rules. So just some things that we need to know about probability, and I'm imagining you guys know some of this already. I know you guys read the book and did the reading guide, but some of the things you need to know about probability. Probability of any event must be a number between 0 and 1. If you prefer percentages, that converts to a percentage of between 0 and 100%. So please, if you are ever doing a probability question and it asks you the probability of something, do not ever give a number outside of that range. Do not ever say that the probability is a negative number. Do not ever say the probability is 1.3, okay? Automatically guaranteed it is wrong. And if there's any partial credit to be given, you will lose all partial credit if you give a completely unreasonable answer like that. So even if you just made a small arithmetic mistake, but you said the probability of something is 1.3, AP exam will give you no credit for that, because you guys should know for probability, I can never get an answer above 1. You can never get an answer above 100%. Okay. Some probabilities that sometimes occur is the probability of something being 0 just means that something will never occur. If the probability of something is 1, it will always occur. Okay, so most things are somewhere in between, but a probability of 0 is an event that will never occur, and the probability of 1 is the event will always occur. So like if I hold my pencil right here and I drop it, the probability is 0 that it will fly up into the air. Probability is 1 that it will drop downwards. So in other words, gravity, it did it. Gravity gives us 100% certainty of what happens when I drop a pin. And I know that it will not float up into the air as long as we are located on Earth. So those are examples of a 0 versus a 1 probability. A sample space is basically a list of all the things that could happen. You flip a coin, the sample space, heads, tails. There's 2 things in the sample space. You roll a die. The sample space is the numbers 1, 2, 3, 4, 5, or 6. Okay. If you flip a coin twice, and you look at what happens when you flip a coin twice, our sample space is now heads, 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 tails, tails, heads, or tails, tails. Those are all the different combinations of what can happen when you flip a coin twice. So the sample space is literally just a list of what's everything that could happen when I do this event. If I pick a student at random from Whitney High School and mark down what year they are, I have a sample space of 4, freshman, sophomore, junior, senior. So whatever it happens to be, there will usually be a finite list of things that occur in the sample space. And the sum of all those probabilities in the sample space must always equal 1. So the probability of heads plus the probability of tails has to add up to 1. So you do not have your entire sample space if you do not have a total of 1. Last example down here is if you roll 2 dice and you add the values the way you usually do in dice games, your sample space is the smallest number you get from 2 dice is 2, the largest number you get is 12, plus you could get anything in between. So our sample space is 2 or 3 or 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so it's literally a list of everything that could happen. Okay, number 3, a complement. Complement is a way of saying the opposite of. And I did move my screen up, but it is not following. There we go. Okay. So a complement of event is the opposite of an event. In other words, it's the probability of the event not occurring. Notation. You will see the name of an event like A with a little c in the corner. It's not an exponent. The little c in the corner just means we're looking at the complement. So right there, we are looking at the complement of A. Okay. And what's cool about complements is sometimes it's easier to calculate a complement by just subtracting from 1. Since the sample space has to total 1, the complement of something is you can subtract from 1. Like if I told you the probability of A occurring is 0.8, 80%, what's the probability that A doesn't occur would be 0.2 or 20%. You just subtract from 1. It's the opposite. So A, if you roll a die and you get a 5, a complement right here would be rolling a die and not getting a 5. So probability of A. This is the probability of getting a 5. Whoops. Dismiss that. Close that. That's usually a sign that things might not go our way here. Probability of A is 1/6. That's the probability of rolling one die and getting a 5. Yep, see, it's not doing anything now. Well, I'll give it 30 seconds and then I'm gonna put it under the camera. There, oh, there we go. Yeah. So probability of A, probability of rolling a 5 is 1 out of 6. Probability of the complement of A, 2 ways you could figure it out. You could count up all the events that are not getting a 5, in other words, getting a 1, a 2, a 3, a 4, or a 6, which is 5 different things out of 6, or you can just subtract from 1. So the probability of a complement, fastest way to calculate it is 1 minus. Yeah, I think I'm going to have to go under the camera because I circled that quite a while ago. Yep, and now I just got the notice that I lost connection. It was good while it lasted. So we're going under camera right here, which means I need camera to the camera. Okay, and I'm going to zoom in and give it a second to autofocus. Okay. I know it gets glitchy online, which is unfortunate. It gets a little glitchy, but it is what it is. It's a little like pixelated there. But you're also following along with your notes, so hopefully the little pixelation on the Zoom isn't bad. Basic addition rule. Okay. If you see a U, that stands for union. In English, we call that an OR. And if 2 events are mutually exclusive, remember that means that they can't occur together, we can find the probability of one or the other occurring by addition. So your key thing that you need to remember is, hey, if I see OR, that's the same as that symbol, and I need to remember that I'm going to be adding stuff together. So when you see an OR, you're going to be adding stuff together. The basic multiplication rule is if 2 events are independent, upside down U stands for intersection. It means and the probability of 2 events occurring together. Again, they're not mutually exclusive because then it would just be 0. But if they're not mutually exclusive, but they're independent, we can multiply and figure out the probability of them both occurring together. So notice down here it says, hey, A and B are mutually exclusive. The intersection, the and, would actually be 0. Because definition of this is they never occur together. So the probability of an and of them both occurring is 0. Okay. So just as a reminder, When you see an or, which is also called a union, just remember that we're going to be adding stuff together. When you see an and, which is also called an intersection, you can multiply stuff together. Okay? Sometimes these probability rules, they exist, but it's actually easier to solve problems if you don't really focus on, well, which rule do I use? And you kind of just think about each problem separately, and usually it makes just more logical sense to do something versus, I got to go look up my formula. So it's better to not focus on the formulas. They're on your formula sheet, so you will have them, but it's usually better not to really focus on them. So just to finish off here, I've got a couple of examples. And then, like I said, you guys will have time to work on, there we go, to work on your chapter 13 assignment. So again, I know it's pixelated for those of you guys online, so hopefully you're just following along on your notes anyway. Okay, a large corporation surveyed its employees regarding the current vacation request policy. 42% of respondents said they were extremely satisfied with the policy. 37% said they were somewhat satisfied. 19% said they were somewhat dissatisfied. And the rest said they were extremely dissatisfied. So, sample space. They took a survey. Sample space would be, well, what are all the possible things that people could have responded? And I can see that there are 4 here. So we've got, oops, extremely satisfied. We've got somewhat satisfied. I'm abbreviating here. Somewhat satisfied. We've got somewhat dissatisfied. And then our last group would be extremely dissatisfied. Okay, so that's my sample space. My sample space is literally just a list of everything that could happen. You respond to this survey. The only 4 things that could happen is you got to respond, one of these 4 things. Or you just leave it blank, and that doesn't matter because that's not considered an event here. Now, if I add on to my sample space and create a table. So let's say I write, these are my probabilities here. Extremely satisfied. That's supposed to be a colon. My probabilities. Okay. Extremely satisfied was 42% or 0.42. It does not matter if you use percentages or decimals. It's completely up to you as far as what your preference is. Somewhat satisfied was 19% or 0.19. Somewhat, oh, nope, sorry, that was wrong. Erase. 19 was over here, somewhat dissatisfied. This one was 37%. And they did not give us the answer over here. However, this is a sample space. What do all of these probabilities have to add up to? 100% or 1. So even though this one was not given to me, I can actually finish this table. This table is something called a probability model, a list of all the events that can happen, of all the outcomes, which is your sample space, with their appropriate probabilities is called a probability model. So if I wanted to figure that one out there on the bottom, all I would do is get a calculator here, and I would do 0.42 plus 0.37 plus 0.19 equals 98%. Subtract that from 1, and I know that over here I've got 0.02. Okay. Now, if it asked you to figure that out on an AP question or a test question, you'd have to show your work. In other words, you'd have to show I added those up and I subtracted from 1. Even though it seems kind of obvious, you do have to show and communicate what you did. But that's how I did it. I just added the other ones up and subtracted from 1. This unit You're going to need a calculator on a regular basis. So if you kind of got used to not bringing your calculator to class in Unit 3, because we literally did not use it at all, you are going to need a calculator when we do Unit 4, because there's a lot of adding and decimals and stuff like that, multiplying. Okay, find the probability that a respondent was at least somewhat satisfied. Now, to me, at least somewhat satisfied means that they could be extremely satisfied or somewhat satisfied. So somewhat satisfied or better. That's what at least means. So they're at least somewhat satisfied. So they could be here or here. So in other words, they could be one of those two things. This is an or. They can't be both because you only got a choice of answering one thing on the survey. So you couldn't answer this and that, but this is an or. So we're really finding the probability of this or that. So what are we going to do with those numbers? We're going to add them. So this is the probability. You don't always have to write the probability out here, but I'm going to tell you what I'm actually doing. Probability of extremely satisfied union, which is an or, somewhat satisfied, is, we're going to add those two together, 0.42 plus 0.37. And we get 0.79. I don't know what that line is right there. Okay. So that's the probability of being at least somewhat satisfied. Somewhat satisfied or more satisfied than that. 3, find the probability that 2 respondents chosen at random. Okay. If we choose 2 people at random, they should be independent, meaning that one person's opinion about this should not affect the other person. You don't choose them at random and they're like best friends and work together and discuss this all the time. They probably influence each other's opinions because that's what people do. A lot of people that, spend time together end up having very similar opinions because we tend to gravitate towards people that are similar to us. But if we're just choosing people at random from this large corporation, they should be independent. So that is why it's important that they are chosen at random. So I now have 2 independent respondents. We want them to both be extremely dissatisfied. So we're looking at extremely dissatisfied, which is right there, but for 2 independent people. So really we're looking at the first person, extremely dissatisfied, and the second person is also extremely dissatisfied. And these should be independent because they're taken randomly. So this person's opinion should not affect this person's opinion. So in other words, first person, 2% chance. Second person, 2% chance. This is an and, the intersection sign is an and we multiply. So 0.02 times 0.02 comes out to 0.0004. So pretty unlikely. That's very close to 0. So pretty unlikely that 2 people in a row would say that they were extremely dissatisfied. Okay, now I'm not going to keep writing all of this because that's a lot to write each time. But if 3 respondents are chosen at random, what's the probability that all 3 are extremely satisfied? Again, they're chosen at random. They should be independent from each other. First person, extremely satisfied, is 0.42. Second person, extremely satisfied, is going to be 0.42. And third person is going to be 0.42. And you guys know from previous math classes that you could write that a lot more succinctly by just doing 0.42 to the 3rd power. It's the same thing. And I definitely need a calculator because I do not know what 0.42 raised to the 3rd power is. But it is 0.0741. You will have to sometimes round like I did right there. Okay, so that is the probability the first person is extremely satisfied, and the second person and the third person, because they should all be independent from each other. Okay, number 3, or part B, none are extremely satisfied. So none are extremely satisfied. So this person is now not extremely satisfied. So I could think of each person not being extremely satisfied as a complement. So a person being not extremely satisfied is a complement. In other words, if you're not extremely satisfied, you're one of these 3 here. So you could just add those 3 because that's all the not extremely satisfieds, or you could just subtract that from 1. And if I subtract that from 1, oops, I get 0.58. Now we have 3 people. We want all 3 to not be extremely satisfied. So the first person, chances they are not extremely satisfied is 0.58. Same for the second person, they're independent. Same for the third person, or use your exponent because it is faster with exponents. And get your calculator out. 0.58 raised to the 3rd power is 0.1951. And here is the most important type of question you could be asked here. Yeah, Celia? You would need to write the mathematics behind it. So you would need to show me where you got this, and then like that. If they are asking you for something here, they will assume that your final answer is what it was asking, but any other steps, if you need to label it, label it. Like, for example, it's good to label that. Probability of a person being not extremely satisfied. So you should label that, and then, yeah, just take it to the 3rd power. Yep. At least one is a very common question. Okay. Now, at least one of the 3 is extremely satisfied. Now, what that really means is maybe 1 out of the 3 is extremely satisfied, maybe 2 out of the 3 is extremely satisfied, or maybe all 3 were extremely satisfied. That's a lot of combinations here. Okay, let's say I decide to call extremely satisfied, because I don't like writing extremely satisfied every time. I'm going to call this event A. So if at least one of them is extremely satisfied, it could be the first one is extremely satisfied and the other 2 are not. Okay, you guys don't have to write all of this down because this is going to be a lot. But don't you agree that that's at least one person extremely satisfied? But it could be this. It could be the first person is not, the second person is, the third person is not. That's also one person that is extremely satisfied. It could keep going, but it could also be 2 people extremely satisfied. And there's a whole bunch of combinations here. It could be that all 3 are extremely satisfied because it just says at least one. Okay, so imagine trying to list all the ways that this could happen and finding each one of these probabilities and then adding them all together because it's got to be one of these. You guys want to do that? I sure don't. So at least one is a pain in the butt to do it that way. So we do not. What we do instead when we see at least one, and this is a reason that it comes up a lot, is because it's super easy to do if you look at the complement. Okay, so the probability of at least one. And this only works with at least one. It does not work with at least two or at least three. It only works with at least one. At least one is 1 or 2 or 3. What is the complement of at least one? Think about that. So at least one means one person is satisfied, or 2, or 3. What's the only one we didn't mention? Okay, we've got 3 people. At least one means exactly 1 is satisfied, or exactly 2, or exactly 3. What's the only other option? Yeah, none of them. At least 1 is the complement of none. Always. Okay? At least 1 is defined as the complement of none. Okay? If I say I have at least $1 in my wallet, the opposite of that is having none. At least 1 means you have some. If I have at least $1, I have some dollars in my wallet. You don't know how many I have. I could have 1 or 2 or 3 or 4 or 10 or 100, but at least 1 means I've got something. The opposite of that is none. Always. So if you see at least 1, please remember that the opposite of that is none. This is much easier to calculate because probability that none of them are satisfied, we kind of already know that. Like in part B, none of the 3 are extremely satisfied. So at least 1 is just 1 minus my answer from B. That's the none are satisfied. So this means I can 1 minus my answer part B, right? Because my none was right there. And I can get my answer to the at least 1 problem. So that's how we will always be doing an at least 1. And again, it only works for at least 1. It does not work for at least 2. It does not work for any other at leasts. But if you see an at least 1, remember that means something. The opposite is nothing, is none. And that is way easier. You only have to do one combination, which is this combination right here. That was the A complement, A complement, A complement. It's one combination versus having to list all those other combinations. So if you don't do it this way, you would have to do it the way I started, which, believe me, is a big old mess because there's just so many different combinations. So they will not ask you to do that with all of those crazy amount of complications. Okay, last question here. Suppose you choose a random U.S. resident over the age of 25. Table below is a probability model for the education level of the selected person based on data from the American Community Survey from 2006-2008. So basically, we've got U.S. residents and we are surveying them based off of the education level that they have attained. So their choices were they have no high school diploma, they have a high school diploma or a GED. So in other words, they've completed high school. The next option up is they've completed some college. They have a bachelor's degree, which is your typical 4-year degree. And then we have some people that went beyond a bachelor's degree and got a graduate, like a master's degree or a PhD or some other type of professional degree, like an MD or something like that. Okay? This is a probability model. Whenever you have a list of all the things that can happen, which is called the sample space, along with their probabilities, this is called a probability model. And what we know is that every probability model, what do these all have to add up to? 1. So I know that the total here has to be 1 because this is a probability model. Every probability model, all the probabilities have to add up to 1. So we can answer part A. What's the probability that a randomly selected person has a graduate or a professional degree? That's the question mark right there. So fill in the space marked with the question mark, show your work. So to figure that out, the easiest way would be to add all of these up. So 0.20 plus 0.22 plus 0.29 plus 0.19. So again, I'm just showing all up. And I know you could do this without showing work, but you do get graded on showing your work. So even though that seems like, well, that's just adding numbers up. Yeah, I know, but write down that you did it. You still have to communicate what you're doing. So that's all of these numbers added up. I know the total has to be 1. So I'm going to do 1 minus 0.9, which is equal to 0.1. Okay. Now notice I did not really label anything, but you can follow along exactly what I did. Someone who reads this can see I'm just adding up all the values in here, and then I'm subtracting that answer from 1. So this is enough work. It's a 2-step process, and you're showing it all. You can even show it all in 1 step if you do 1 minus parentheses all of those. So if you want to show it in 1 step, that's fine, but just make sure it's mathematically sound the way that you choose to write it. Okay, what is the probability that a randomly selected person has at least a high school diploma? Now, at least a high school diploma means that they have a high school diploma, or they have also had some college, or they have a bachelor's degree, or they have a graduate degree. And remember, we just figured out that this one was 0.1 here. So one option, I can add all of those together, because at least a high school diploma means they are here or here or here or here. You can't be in more than 1 spot because you're defined by whatever is the one that describes you. So I could add all 4 of those together, or since the whole thing adds up to 1, I could just subtract the 0.20. Either way works. So either add up all the stuff in yellow or do 1 minus 0.20 and we get 0.8 or 0.80, same thing. So show your work. If you did the 1 minus 0.20, that's the quickest way to do it. But if you didn't, just show that you added up all of those yellow values and you should still get 0.8. Okay, part C. What is the probability that 5 randomly selected people, so again, they're independent, all have at least a high school diploma? Well, there's the at least a high school diploma. We want 5 people to have this. So, since they're all independent, I'm just going to multiply. So 0.8 to the 5th is the easiest way to show it mathematically. There's 5 of them, and it's an and. The first person has at least a high school diploma, and the second person, and the third person, and the fourth person. 7, 6, 8. Okay, so it's an easy calculation on a calculator. Not so easy without a calculator, so you definitely need a calculator for that. And then D. What is the probability that of 5 randomly selected people, oh, here it is again, at least 1 has a graduate or a professional degree? So at least 1, okay? At least 1. Whatever it is, at least 1 has grad or professional. That's the very last entry in my table. Okay, at least 1 has a graduate or professional degree. We are not going to do this as an at least 1. We are always going to do the complement. And the complement of at least 1 is always none. So none have grad or professional degree. Okay, so 1 minus. Okay, my first person, because none of them are going to have a professional or a graduate degree. The first person does not have a professional or a graduate degree. So that means the first person is not here. The first person is here. So we have to add those numbers up, which we already did in the first one. I know that those numbers here add up to 0.9. So if you do not have a graduate or a professional degree, the chances of that are 0.9. And we want none to have a graduate or a professional degree. So there's my first person. That person does not have a graduate or a professional degree. The chances of that is 0.9. Same for the second person. Same for the third person. Same for the fourth person and the fifth person. So the easiest way for me to calculate this is just to do the none for all 5 and then subtract that from 1. And that none thing can be confusing, the at least 1. So 1 minus 0.9 raised to the 5th is 0.40951. Okay, now chapter 13, and that's it, yep. So chapter 13 is the beginning part of probability. So what you need to know from chapter 13 is, just basic rules of probability. Every answer is going to be between 0 and 1. If you see an or situation, you're going to be adding stuff together. If you see an and situation for independent events, which they're all going to be on chapter 13, you can multiply them together, but you are going to also see the at least 1. And that's probably the trickiest thing, is realizing the at least 1 is really just a complement. Remember, a complement means the opposite of, so you subtract from 1. Okay, so we have about 20 minutes left. Okay, so if you guys are online, 20 minutes, you guys can start working on your chapter 13 assignment, which is in MyMathLab. And the guys that are here, all we're going to do today is take the next 20 minutes and just jump on the assignment. Okay? And of course, if you have any questions, please let me know. Okay, but that's what I would like you guys to do. And you'll notice that there is a spot in Schoology to upload these notes. So once they're filled out, and hopefully they're out now, should have just been going along with me, but turn these in on Schoology. You get credit for doing the notes with us. And then you can start working on the assignment on MyMathLab. In the Zoom call, but you can stay in if you need to ask me questions or anything like